Hello and welcome. Today we're going to talk about basic principles and the practices of clinical chemistry. So these are the objectives. I'm going to go ahead and let you guys read through those. All right, so reference materials. These are materials that we use in the chemical or chemistry lab to help us determine what is needed for testing. So reference materials, we have a primary and secondary standard. So primary standard is a chemical that can be measured directly that produces an exact known concentration, but these are usually unavailable. So we usually will use stuff like a secondary standard. They usually have a lower purity, and the concentration is going to be determined by comparison to the primary standard. The standard material should be of the same matrix or the same type of specimen. So if we have a urine specimen, that reference or secondary standard should also be a urine, and same goes for if it's a serum or a plasma as well. So solutions, solute, if you remember back to your original, chemistry class, solute is a substance that is dissolved in a liquid, also known as an analyte in clinical chemistry. Solvent is the liquid in which the solute is dissolved, and then the solution is both of those combined, so the solute and the solvent. So concentration. So percent solutions, these are based on the idea of parts per 100. That means how much solute is present in every 100 parts of the total solution. There are three common types that we will use. Well, the first one is a weight, and that is the grams of solute per 100 grams of solution. And then volume is the milliliters of solute per 100 milliliters of solution. And then our last one is weight and volume, and that is grams of solute per 100 milliliters of solution. So just make sure you pay, close attention to those. If it's a weight, it says grams. Volume, it's milliliters, things like that. These are especially useful in biological and medical sciences where exact proportions are going to matter. And then we have molarity. Molarity refers to the number of moles of solute per 1 liter of solution. 1 mole of substance is equal to its gram molecular weight, also known as GMW, and it's also called molar mass. We like to have multiple names for things in science. The units of molarity are mole over liter, or sometimes millimole over liter in clinical settings. So if I dissolve 1 mole of sodium chloride in 1 liter of water, I will have a 1 molar solution. Then we move on to normality. Normality is a bit more specific and is based on the equivalent weight of the solute. Normality equals the grams of equivalent weight per liter of solution. The equivalent weight is the molecular weight divided by the valence. What is the valence? The valence refers to the number of hydrogen ions the substance can donate, accept, or react with. So for example, we have sulfuric acid. It has a valence of 2 because it can release 2 hydrogen ions per molecule. So in summary, we have percent solution equals the amount of solute per 100 parts of solution. Molarity is the moles per liter. Normality is the equivalence per liter, which is based on how many reactive units the solute can provide. Buffers. So what are buffers? Buffers are solutions that contain a weak acid or a weak base along with its conjugate salt. Their main function is to minimize changes in hydrogen ion concentration or pH when small amounts of acid or bases are added. This is essential in biological systems where enzymes and processes are going to depend on maintaining a stable pH. So how do buffers work? So a weak acid partially dissociates in solution, and that releases hydrogen ions. Its conjugate base can neutralize added hydrogen ions, which can resist a drop in pH. So likewise, if a base is added, the weak acid donates more hydrogen to neutralize the hydrogen ions, minimizing a rise in pH. So we show this by the Henderson-Hasselbalch equation. So this helps to quantify the buffering action, and that is the equation there. You don't necessarily need to know how to solve for it, but I would definitely know what the equation is and recognize it for the test. So pH, that stands for pH. That is the current acidity of the solution. The pKa is the acid dissociation constant, which is a measure of the acid strength. The A negative is a concentration of the conjugate base. The HA is the concentration of the weak acid. This equation helps us calculate the pH of a buffer solution and shows how the ratio of base to acid can help influence the pH. So some takeaways from this, we have the buffers act as a chemical shock absorber for pH changes. And then the Henderson-Hasselbalch equation is the tool that helps us understand and design effective buffer systems. Water specifications. So there are different types of water that we use within the clinical lab. So we have distilled water that is purified by distillation. Then we have deionized water, and that is purified by ion exchange resins. And then we have type 1, 2, and 3. Type 1 is filtered, and that helps to remove particulate matter. Type 2 is acceptable for most analytical procedures. So this is the one you're going to kind of hear about besides like distilled and deionized. And then we have type 3, and this is used for glassware washing, but we don't use it for analytical procedures. Glassware, so as I'm sure you are well aware, is different glassware as well that we use in the clinical lab. So I'm sure you're familiar with glass tubes and flasks and things like that. But this glassware is made of different types of glass. So lots of times it is a high thermal borosilicate or an aluminosilicate glass. It has to meet the Class A standards that are set by NIST. And NIST is the National Institute of Standards and Technology. So we also have plasticware that can be made of styrene, polyethylene, and polypropylene as well. And then lots of times you're going to want to immediately rinse these after use. That helps to get it clean and not absorbed, especially for the plastics. For pipettes, there are different types of pipettes that are also used. The pipettes are usually used to transfer liquids. So to contain, which is a TC, or to deliver, which is a TD. So you can see the proper techniques and how to use them in your textbook. Lots of times some of the glass ones will have etched rings, and that means that they are a blowout type of pipette. If they do not have those etched rings, that means that they are self-draining by gravity. And then we have serologic pipettes. They usually have calibration marks, and it also means that they're a blowout. And then you have volumetric, which is usually one volume types, like 1 milliliter, something like that, and it is self-draining. These are the calculations that I would review from your textbook. You may need to know some of them for the exam. Just make sure to look over the exam review document that is found in your module.